have set those in the back. I think we're set. I don't know what happened, but we'll find out. Cool. Oh, can you drop the lights too? Somehow. We never know what we're going to get. Yeah, not so that just above the fall asleep threshold. I'm not sure what we did before. One of them's, are they up here?
I just kept pressing buttons until things happened. This is pretty good.
Is that okay?
You guys want to fall asleep?
All right. So I'll
Anyone need any handouts?
just leave them in the back because sometimes one or two people come in a little on the late side or whatever. Yeah, sure. Okay, cool. It's crooked. That's right, I'm not going to perseverate. Okay, so welcome back, week 2, right? So this is sort of the continuation of our sort of hardware lectures. And what we'll focus on today is the B1 system. The primary responsibility of the B1 system is to do what? Anyone know? I have a one word that I usually use. Thank you. It's the exciter, right? So B0 is the polarizer. We talked about sort of the NMR phenomena in the last lecture. And today we're going to talk about B1, which is mostly used as the exciter. Serves some other purposes as well, and we'll talk about some of those as we go. Really quickly, I got an interesting question sort of at the break and stuff like that. So I try to come back to these things when I can. And someone said, well, hold on. You went on and on and on about spin and charge and spin and charge. And you need spin and you need charge to have a magnetic moment. And this very smart person came up and said, well, hang on. What about the neutron? The neutron has no charge, but it has a magnetic moment. So how is it that it could have no charge and it has spin? How could it be that it has a magnetic moment? And this gets down into the muons that are the subatomic particles, rather, that are within the neutron themselves having spin. And so the ensemble total amount of spin comes from the subatomic particles and ultimately gives it a charge of 0, but a spin of half. So not an obvious answer. And then if you want to know what happened, why does that have a spin of half? We're going to shut the door, right? We have to go the other direction. I like these questions, great questions, but we got to move up to the sort of higher levels. So then quickly, our learning objectives from the last lecture. Hopefully you understand that there were sort of 3 main principles of the B0 field, that it acts as a polarizer, it's pointed along the z direction, it gives us this net bulk observable magnetization. We move away from the magnetic dipole to talk about the bulk magnetization, Avogadro's number of spins, right? And then it's responsible for the precessional behavior that we typically think about when we think about MR, and we'll discuss more today. And you should have some understanding about Zeeman splitting as well, right? Spins can be in the spin up or spin down state, and there's just barely a difference between these two populations. If there was no difference between these two populations, would we be in this class? Probably not. There'd be no observable phenomena, right? So because there is this slight difference between the spin up and spin down state, there's something to observe, and what we observe typically is the behavior of the bulk magnetization. We'll talk about this some today, but we're going to come back to the equation of motion. We talked about the equation of motion for an ensemble of spins. We had this system of differential equations, and we went through a bit of work to come to a solution for, if under some conditions, what is the spin's behavior as a function of time. We're going to do that again today. We talked about free precession, and we talked about that in the laboratory frame. Today we're going to introduce the rotating frame when we get into the spins and move with them at the Larmor frequency. And we're also going to talk about not just free precession, but we'll talk about forced precession. So that gets us to our next learning point here, which was differentiating between free and forced precession. What was free precession? Does anyone want to give one sentence? Say it again. So I would say it differently. The free precession is what happens when we're not acting on the spin system, right? It's been acted upon previously, maybe by an RF pulse, maybe by gradients, maybe by something else. But it's the behavior of the spin system just in the presence of B0. They're just free to do what they do. Relax, spin, whatever. We haven't talked about relaxation. That's coming next time. So that's a distinction of forced precession. So forced precession is we're forcing the spin system to do something, and that's typically done through RF pulses. We'll talk about that a lot today. So we can force the spins to go from their equilibrium position, which we think of the bulk magnetization as pointing straight up. We can force it over to the transverse plane, or in fact, we can invert the spins and do any number of other things with them. And then we did in the very sort of end of that lecture, middle end of that lecture, we were solving for the bulk magnetization dynamics under specific conditions. And we're going to do more of that today. And this is something we're going to do a fair bit of, because it's the only way you can really understand how this NMR system sort of works and operates, is if you can write down the system of equations, solve those system of equations, and say, okay, that's what the spin system is going to do. And in fact, each of you will get to the point where you can simulate these things as well. That's where MATLAB really comes in. And we may not get to talk about MATLAB much today. There will be small elements of which you'll need it for the homework, and then some more complicated elements you'll need for the homework as well, and I'll try to give some background for that, at least in the next assignment. So then this is maybe the summary of where we were, right? We had several equations that described, the torque of the magnetic moment in the B field, the definition of torque itself, angular momentum, and then this empirical relationship that tied together the spin angular momentum, the magnetic dipole to the angular momentum through the gyromagnetic ratio. And we worked through some steps where we could get this equation of motion, and at the beginning it was just the equation of motion for a single spin, which doesn't really make a lot of sense. A physicist would really sort of be offended by that. But that's okay, because we said, well, we'll step away from that and we'll just add everything up. We have 1 million, 1 billion, 1 trillion more of these spins. We'll add them all up and we'll give ourselves a new equation of motion for the bulk magnetization. And we're going to see this expression show up again today. What coordinate frame is this system of equations describing the bulk magnetization's behavior in? What coordinate system? The laboratory frame, right? And so today's job, and we'll get into it as much as we can, but today's job is to transform that set of differential equations into the rotating frame, where now we're suddenly moving with the spin system, because it turns out things are mathematically a lot more convenient, and it's kind of just easier for us to observe and understand if we're in that coordinate system. Given a system of differential equations, we had to apply some boundary conditions. We had to say, well, what is the B field acting on this system? And the simplest system for free precession is just saying, well, the B field we care about is the B0 field. It has a magnitude, and it points along the Z direction. And we could plug that in, right? So this is the same system of equations for a specific B field that we care about. That specific B field only has a single component, so it only fills in this one spot in this system of equations. We can take the determinant of this thing to end up with 3 differential equations, and then we work towards solving that system of differential equations. And the result of all that work was to say, well, we know how to describe the mx component, the my component, and the mz component for free precession in the laboratory frame. And under those circumstances, what you see is that the mx component of the magnetization is just going to be oscillating back and forth. It has a little bit of a complicated sort of cosine and sine term associated with it. That really depends on the initial conditions, right? And so if the initial condition were such that the my magnetization were, say, 0 after some pulse, then this term would just go away, because you'd have no my superscript 0. And if you don't have any my superscript 0, then this term also drops out. And so you can more easily maybe see that mx is just going to oscillate like a cosine, and my is going to oscillate like a sine. So that gives us this idea that the magnetization is going to be running around in a circle, right? Precessional behavior, if you will. And then under these conditions, at least, laboratory frame, no relaxation, the mz component of the magnetization is just a constant. We have some mythical, magical condition where the state of the magnetization is such that it ends up tipped over. And under these kind of arbitrary conditions, it will just stay with that component of the mz magnetization forever, right? It's not a real situation, but it's a useful mathematical example. Questions about sort of what we covered in the last lecture, or where we ended up? We're going to work through a bunch of this, so if, or many examples like this. So if this is confusing, if there's aspects of this that you don't understand, that's something you want to get back to. I'm less concerned with sort of like the details of solving the differential equations. I'm more interested that you understand how to set it up, how you can set up the system of equations from this sort of basic expression, and then understanding what maybe the solutions look like. This isn't a class on differential equations, so the solution strategies I'm not quite as picky about. You'll work with them some, but that's not the focus. Okay. So then the question for today is, how do we actually perturb the equilibrium, right? How do we go from having the bulk magnetization pointing straight up to some other state where it's pointed in some other direction. So we'll talk about perturbing the equilibrium through the use of an application of RF pulses. Later, we'll talk about how we return to equilibrium through the process of what's called relaxation. We won't get to relaxation in this lecture, though. So in the last lecture, we talked a bunch about free precession in the laboratory frame, and I said there were really 4 conditions that we care about preliminarily. Today, we'll talk about forced precession in the lab frame. That goes quickly, because we'll end up with a system of equations that's kind of complicated, and we'll say, you know what, let's try doing this a different way. And that's what sort of encourages us to think about the rotating frame. And then today, we will work through free precession, writing out the expressions for free precession in the rotating frame and forced precession in the rotating frame. And again, this is all without relaxation. We haven't introduced that concept yet. So I think maybe something got cut off on the bottom there. Yeah, there were 2 reasons for this, right? Relaxation time constants are really, really, really long, so there kind of is effectively no relaxation. Or the other one is that the event time scale we care about is just a lot shorter than those time constants, sort of the 2 different extremes. Okay, so this is where we are in working our way through this sort of longer diagram of how an NMR system converts the magnetic dipoles to images. We're, week 2, we're getting there, right? And the idea today is to really talk about how we can take the bulk magnetization, which is a three-dimensional vector, could point in any which direction, and how we can act on it through an RF pulse here, a B1 pulse, using the B1 field to generate some transverse magnetization. And again, why was it so important to generate transverse magnetization? What's that? It's the most detectable. That's exactly right. The way these systems are put together, designed, set up, like we are sensitive to detecting MXY. We're basically, this comes much later in the class, we're basically insensitive to detecting changes in MZ. Now, that's a confusing statement if you know a little, but maybe not a lot about MR. So let's just leave it at the idea that it's the transverse magnetization is what we detect. Now, the job of MR, and we haven't gotten there yet, but the job of MR is how to encode all the information we care about in the transverse magnetization. And it turns out you can actually store things about the Z magnetization in the transverse magnetization. That's not an obvious concept, but there's a way to do it, and we'll get there. So this is what we're really talking about today, is this B1 system. Okay, so a bunch of learning objectives. You can sort of keep these in mind as we go. I'm not going to go through these sort of carefully now. We'll try to come back to them at the beginning of the next lecture to see if we're there. Again, the point of me putting these together is when you go back over your notes or you're trying to figure out homework problems or how to study for the final, these are the things that I think are important in having put together the lecture. Okay, so just like in the B0 lecture, and as you will see in the gradient lecture, there is a slide a lot like this where it says the B1 field is A, and there's a B0 field is A, and the gradient field is A. And so these are things that I consider really important, especially kind of the values and the numbers in these. And the reason for this is we really have 3 different scales of magnetic fields that we use in MR. With the B0 field, does it change with time? Does it change with space? Not really, right? So it's pretty boring, right? It's static, homogeneous, under ideal circumstances, right? Well, B1 is way on the other end of the spectrum, right? It's in fact, it's a magnetic field in the radio frequency range, meaning it's oscillating at very, very high frequencies. And the whole principle is that the radio frequency's frequency has to match the Larmor frequency to engage with the spin system. And so we know we're going to be in the neighborhood of 42.58 megahertz per Tesla, and then it depends what field strength we're operating at. So we know we're in that tens of megahertz, hundreds of megahertz, even approaching a gigahertz on some systems. And so that's why it's called an RF pulse. And the reason it's really called a pulse is they're typically very short in duration. We turn them on, we turn them off. And we do this a lot during an MR imaging experiment. We have to excite the spin system, get a little bit of information, excite it again, get a little bit of more information until we have all of the information we need for the entire imaging experiment. So we typically just call these RF pulses. Hundreds of microseconds, maybe a few milliseconds, kind of ballpark. You could have really short RF pulses, you could have much longer ones, but this kind of ballparks it for you. So highly time varying, very short in duration, and also very small in amplitude. Right? So these pulses are going to be less than 30 microtesla. In fact, a lot of systems can't even generate a 30 microtesla field with their B1 coil. there are 5 microtesla fields or 10 microtesla fields. Maybe 20 is going to be used with some frequency. So I want you to appreciate these values because they're so completely different, right? We're engineers or physicists or chemists coming from different backgrounds, but we want to appreciate the orders of magnitude and difference of this B1 field compared to the B0 field. Something that we'll introduce in just a second is the idea that this field is so-called circularly polarized, okay? And I'll give you a description of what I mean by that later. Effectively, it means that it's a B1 field that's rotating at the Larmor frequency. It has to be able to engage that spin system. So if my spins are rotating at one frequency, my B1 field has to oscillate at that same frequency to put energy into that system. That's the resonance phenomena, right? These are, of course, magnetic fields, and then we'll see mathematically in a little bit here, they're perpendicular to B0, right? So the directionality of these fields matters a lot as well. These are not K-directed B fields. These are I and J directed B fields, and we'll talk a lot about mathematically what that looks like as we go. So how do we generate these fields? Well, here again is sort of the hardware teardown of what's inside of a scanner. We've talked about, you know, the cryostat that contains the main coil, the B0 coil already. That's sort of the outermost layer of the scanner, if you will. Concentric and inside of the B0 field are the gradient fields and also the body, what we call the body coil. It's a lot of nomenclature. I'm trying to use the familiar terms and the most common terms as best I can. We oftentimes call this the body coil. Don't confuse that with the receiving coil, which we'll talk about later. You put a receiving coil on the body part of interest. There are so-called body coils or body arrays as well. What we care about here is that this B1 system, which we usually call the body transmit system, it can, under some circumstances, be used for reception as well, but what we care about today is this hardware component in the middle here, which is the body coil. It's the B1 system, and it generates the RF pulses. It's also located sort of concentric about isocenter, right? We know our B0 field is best and sort of most uniform at isocenter. Our B1 system is designed to operate specifically in and around isocenter as well. This B1 system is not way down by your feet. It's not way up at your head. The anatomy of interest is advanced to isocenter because that's where the imaging conditions are most favorable. So we move your head to the middle of the scanner, your feet to the middle of the scanner. Okay, so the most common design for this is what's called an RF birdcage coil. If you come from an EE background, this is perhaps a familiar design already. It's a highly efficient design, which means nearly all the fields produced actually contribute to imaging. So that's a good thing in terms of sort of energy efficiency and sort of overall electronic design. It will generate a very uniform field. So this is a teardown of the coil that's sitting inside the scanner. They call it a bird cage just because the copper elements sort of look a little bit like a bird cage, right? And the patient is going to slide sort of inside on a nice comfortable scanner bed, slide inside this B1 coil. Outside to the B1 coil is the gradients. Outside to that is the B0 field. We'll come back to gradients later. It's a very uniform field, especially radially, so meaning in some concentric kind of circle, even a sphere near isocenter. It generates a very uniform B1 field at every spatial position. It does decay axially, so it's sort of falling off as you go towards someone's head or towards someone's feet. So again, it's really focused or designed to have its best operation at isocenter. And it generates a pretty uniform B1 field over a sphere, if the length is approximately equal to the diameter. So these B1 coils themselves are maybe 60 or 70 centimeters in diameter and roughly equivalent in length. And what it does is it generates, this coil by design generates what's called a quadrature field or a circularly polarized field. And we'll talk about what that means in just a second. But the idea is that the B1 field itself, in the laboratory frame, if I'm standing next to the scanner, the B1 field itself is pointing in a different direction constantly, right? It's rotating around at the Larmor frequency. So at 46 or 64 megahertz, 128 megahertz, it's precessing around. And this coil is designed such that it can produce, in principle, either of these circularly polarized fields. And you can have left-handed polarization, or you can have right-handed polarization. And I'm going to talk a little bit later about why that's important and which one we choose to use. Yes, please.
The length represents the length of the coil?
In this diagram here? Yeah, this is actually time. That's a great question. So not very obvious. So the idea is that, let's say X and Y here, this point represents isocenter. At isocenter, if you just watch this circle here, you'll see this bigger vector is rotating around. That means at isocenter, the B1 field is constantly pointing in a slightly different direction, right? It's a little bit of a confusing diagram, but I either have to remake it or take it from, I think, Wikipedia. Good?
There's a temporal frequency and also a spatial frequency, so it should be the temporal frequency match the normal frequency, right?
Yeah, we haven't gotten to spatial frequencies yet, yes. But the temporal modulation of this B1 field is oscillating at the Larmor frequency. And you'll see more of this mathematically in just a second. I'm trying to give the kind of qualitative perspective to begin with. Okay, so this is what the process of excitation looks like in the laboratory frame, right? So this is a scanner. I'm going to lie down. I'm going to go in head first. And we could, for example, look at a slice through this patient here. And what we just saw there a second ago was the process. This is simulated using the equations that describe excitation and relaxation, what happens to the spin system. So let me just go back a second here. So imagine I play an RF pulse. My RF pulse, you'll see these start wobbling around in a second. They're wobbling around. They're trying to precess, but there's energy going into the system such that eventually they start to tip over. And now they're in the transverse plane. They're pointing in the transverse plane and precessing around. And it's during this period of time when they're precessing in the transverse plane that I can detect some signal and then try to make sense of that signal. The sort of middle third of this class is how do we interpret that signal to begin with. So this is the process that we want to describe today. How is it that RF energy can tip the spin system over? And that's kind of qualitatively the picture you can have in mind. Well, that's fancy. Okay. Oops. So I want to make a distinction too, because I think it's a good one. So we already know that protons, or H1, has intrinsic spin, right? This is maybe a new physical property or chemical property that we learned about the hydrogen nucleus. We also learned a lot about precession. And so I made a distinction between spin and precession. They sound kind of the same. We might colloquially use them similarly, but mathematically or in this class, they mean very different things. During the process of excitation, especially if we talk about observing it in the laboratory frame, it's the B0 field that will impart the precessional behavior, what we think of as the sort of wobbling around at the Larmor frequency. The B1 field, it still has to follow the same physics, right? It's just a B field. And so that B field multiplied by gamma will define another precessional frequency. And that precessional frequency, is it going to be higher or lower than, say, omega 0? Lower. Why? You're right. So B1's small, right? It's like microtesla, right? So Tesla versus microtesla. Omega 1 is going to be slow compared to omega 0. So where omega 0 is on the order of megahertz, this is going to be on the order of hertz, right? But they're coupled together. The protons just respond to magnetic fields. And now I'm applying magnetic fields at very different time scales, if you will. A constant high magnitude field and a time varying low amplitude field. Spin system has to be governed by both of those. And what the B1 field governs is usually what we call nutation. And nutation is just sort of, in this example here, it's shown kind of, don't take this too literally for MR. Nutation here is shown as kind of wobbling around the precessional axis, right? That's not exactly what I have in mind for MR. Nutation for us means that the whole thing tips all the way down, that the wobble is so big and so low in frequency that it wobbles down to the x-axis, or it wobbles down to the y-axis. Okay, so if you look at this red sort of modulation here, this is kind of a high frequency modulation or somewhat high frequency modulation. Imagine if it only went through a nutation of, say, pi over 2 in one revolution, then the magnetization would bam hit the y-axis or maybe the x-axis. So again, think in terms of scales a little bit here as we work through some of the next problems, and appreciate the difference between spin, precession, and nutation. Is nutation clear? I haven't presented it this way before, so I want to make sure that that's an okay concept. We're just talking about the bulk magnetization moving away from that z-axis, right? Really pushing it away through the process of forced precession with a B1 field that'll tip it all the way over. Okay. So this is what's happening to the bulk magnetization, again, in the laboratory frame. I'm putting RF energy in at the Larmor frequency, and every time it swings around, I'm sort of pushing more energy into it, right? Let's go back one more time. So here it's coming this way, and I'm going to push it that way and it's going to fall down some more, and I'm going to push it again and it's going to fall down some more, and I'm going to keep pushing on it as much as I need to until it's gotten into, say, the transverse plane. At the end of this example here, we see the bulk magnetization is lying along the x-axis. So we can talk about how far we tipped it down. And how far we tipped it down we refer to as the flip angle. And in this case, the flip angle was 90 degrees, right? It went from pointing straight up to being effectively tipped over by 90 degrees. Now, this sort of spiraling behavior is the combination of precession and nutation. A little bit complicated to look at, a little bit complicated to write down mathematically. I'll show you where the expression for this comes from in just a second, and then we're going to give it up. Because all we ultimately care about in MR is where did the magnetization end up. And in this case, it ended up in the transverse plane, so maybe there's a simpler way to describe that. And in fact, there is, and that's what will take us from the lab frame into the rotating frame. Yeah? Okay, so let's look a little bit more at this RF birdcage coil. The idea is you have these copper rungs, end rings and rungs that sort of bind the whole thing together, separated by capacitors. Another way to think about it, think of each of these sort of pluses as being one of the rungs, and I can drive current through one of those rungs if I want to. And so let's say I'm going to put some current into the page. B fields will observe the right-hand rule, so I can put current into, say, my first source up here, and I'll generate a B field in that particular element. If I generate a B field on that particular element, it's pointing, at least on the inner part of that rung, it's sort of pointing in the, say, towards the left or in the minus x direction. That's going to exert a torque on M, right? B fields that are perpendicular. This is a magnetic field, that's a magnetic field. If they're perpendicular to each other, I'll exert a torque on M. And so that's why, at this point in time, M is just pointing, say, out at us, right? We're looking down the z-axis of the scanner, right? As soon as I energize that rung, I can create a B field that will slightly push my bulk magnetization vector over. I'm discretizing this into like really small sort of time events. So current I1 induces this left-handed nutation about the B1 field. So I push over M1 a little bit. In the next little element of time, though, it's obviously going to precess, right? The B0 field says, well, I'm not going to stay there. I'm going to start zipping around at 64 megahertz. So now I have to make sure I switch on this current over here. If I switch on this current over here, I can generate a B field. That B field is perpendicular to M, and I can push it over some more. And so I'll generate even more transverse magnetization. And I can keep doing that. I can basically, the electronic design is a little bit different than this, but the idea is I can put an oscillatory current in my first, second, third, fourth, fifth, and sixth rungs such that I can engage the spin system in a resonance fashion. I have to be at the right frequency, and I have to effectively chase the bulk magnetization around in this, in this sort of left-hand sense. So the current that you actually need to drive that system looks something like this. It has to have some amplitude. We'll talk about the amplitude in just a second. We could drive it with a sine wave. Why not? It has to be at a particular frequency, which we call omega RF. We'll see in just a second, but the omega RF has to be matched to the Larmor frequency, or ideally it's very, very close to the Larmor frequency. And then the amount of current phase, meaning how out of phase these individual elements are, is just governed by maybe how many rungs we have in our B1 coil. So we could have 16 rungs, or 8 rungs, or 32 rungs, or whatever. So conceptually, does this kind of make sense? I'm going to generate B fields that effectively let me chase my bulk magnetization and push it into the transverse plane. And so this is why we say that the B1 field as a function of time is circularly polarized, right? We're chasing it around in this sort of circular fashion, if you will. There's a lot more information about these kinds of things. One of the things that you can wonder is, well, how much current do I have to put into this system to get there? And that requires some kind of calibration, right? So there's no closed form solution for that because it depends specifically on the design and physical implementation of the design that you make. But there is some connection, we'll look at this a little bit today, between the current that you need to drive it with, the duration of that current, and where your spins will end up. Right? So if it's a low amplitude, if it's no current, nothing happens. If it's more current, I can push things faster, right? And then the duration that the current is on is determined sort of how far things will get towards the transverse plane. I don't always want to get to the transverse plane. Sometimes I just want to tip 10 degrees. Sometimes I want to tip 180 degrees. There's different circumstances for that. But conceptually, this is what's happening. Yeah?
Just to clarify, if these different longs, they
Well, I mean, I wouldn't refer to them as switching on and off sequentially, but rather being driven by currents that are governed by some sign or some specific frequency, and they all have slightly different phase, right? So the current in the nth rung has a different phase than the 0th rung or the first rung or the second rung.
So there are just difference in the phase. But
Correct.
turn off the amplitude of the current. It doesn't turn off.
Yeah. So that gets into the design of the B1 field itself. So, and we'll see this some today, but the B1 field, we can turn it on, turn it off. We can also modulate that so that the I0 function here could itself be a function of time.
Yeah, I mean, when transmitting the B1 field, it doesn't turn off.
When you're,
Turn off. It's not like turn on one run and turn on the other run.
that's right, yeah, there's no turning on, turning off. You basically gate this current. You're basically gating this current, but you can, this I of 0 could be a function of time. And at some point it's on, and at some later time it's off, but on the scale of like milliseconds or something like that. Yeah? Okay.
Could you clarify again in this figure the direction of the arrow? Is the direction or inside the coils?
So,
The arrows.
which arrows?
Is the XY plane or
I'm so sorry. Yeah, so hopefully I had it in one of the earlier sort of slides, but this would be the transverse plane. This is the XY plane, right? So just like this example here, and I'm sorry it's not labeled, you're right. This is also looking at like an axial slice. What this is showing here is some simulation work, not from our group, from another group. It was labeled on a previous slide, about the uniformity of the B1 field that you get with this kind of design. So it's non-uniform in places you don't care about, way out by the edges of the coil, but it's quite uniform, say, across the head itself, for example. Yep.
So real quick, just to clarify, the reason we need to like switch off the rungs is because they only provide like force on the bulk magnetization when it's perpendicular. Is that what it was?
Yep. And so if the B1 field is perpendicular to the M1 field, there's no torque. Right, so it was mu cross B gave us a torque, right? We had an expression maybe 2 lectures ago, I forget a little bit, but the torque acting on the spin system was mu cross B. In this case, what we're talking about is B1, right? So if the mu vector and the B1 vector are parallel, then they don't act on each other, or there's no torque exerted. We have to exert a torque to get this thing to do something. Okay. And again, don't so much think about it as like sort of turning them on and off. You're just you have an oscillatory current, and they're out of phase between the different rungs. Okay, so interesting problem, and this is sort of a terminology thing, but something to keep in mind is that we want that B1 field to be homogeneous, right? If I'm coming up with a sequence and I want a 90-degree pulse, I want a 90-degree pulse everywhere. Right? Now, of course, there are reasons systems behave imperfectly, or the imaging experiment itself can be imperfect. And one of those reasons is the so-called idea of B1 inhomogeneity, right? We refuse to use the word heterogeneity. Don't know why. So B1 inhomogeneity. So that means we have an imperfect B1 amplitude as a function of spatial position, right? So I want 90 degrees across, say, my whole image to tip everything over, the same amount. But for some reason, and that can be a consequence of the interaction of the subject and the coil themselves, right? Things about the conductivity and permittivity of the subject or the object that you're imaging. So these become real challenging problems to sort of avoid. We have hardware imperfections, and in fact, we can have so-called wavelength effects as well. But just to show an example, you can have wavelength effects or B1 inhomogeneity that'll give you regions of an image that are non-interpretable. They're just dark for some reason, or they could in fact be hyper intense. But when you get really sort of structured variation in your signal intensity, one source of that can be so-called B1 inhomogeneity. These guys had an interesting strategy. I'll leave the paper to you guys if you want to get back to it or talk about it with me. But they had an interesting strategy for manipulating the permittivity such that they could arguably sort of correct or fix these so-called wavelength effects. So again, just remember that the systems are imperfect, right? We want it to be perfectly uniform B1, but we don't always get that, unfortunately. Okay, so this brings us into this idea of resonance. We've talked about generating a B1 field, and I've said we need that B1 field to generate some transverse magnetization. Let's talk a little bit about what's happening such that we engage this so-called resonance phenomena. This is, I think, a good movie that's borrowed from this Hansen paper from several years ago. In that paper, he says that the equilibrium magnetization is stationary. So even though the individual spins are precessing, there's no net emission of radio waves in equilibrium. So if you picture some voxel, some volume of interest that we care about, millimeters by millimeters by millimeters, you have Avogadro's number of spins in there. You can see he's done this carefully such that there's a preponderance of spins in the spin-up state, and it's slightly less dense in the spin-down state. And the consequence of that is we get a net observable bulk magnetization. That's this top vector that's pointing out. This is the M vector, if you will. And this is just what happens to an ensemble of spins when exposed to B0, right? Some spins have slightly different phase. They're all trying to precess around at the Larmor frequency, but there's nothing that's organized them in any coherent way such that their transverse components just cancel each other out, whatever they are. There's enough of them randomly oriented such that they cancel out, except for in the z direction. So this is the concept, sort of, it's one arguably good enough picture of what's happening to a many spin system to give us so-called bulk magnetization. There's different ways to sort of think about or understand the sort of resonance phenomenon. It'll relate back to that diagram in just a second. In quantum physics, we would say that the electromagnetic radiation, given that it has a frequency omega RF, this is the energy we're putting into the system, carries energy such that it can induce a transition from the spin up to the spin down state. So that'll give us enough, that'll give us more bulk magnetization that's observable. Really hard to bridge, again, between quantum and classical physics. In the classical sense, and that's really what we're going to use, basically from today, we'll leave all things quantum behind. The B1 field rotates in the same manner as the precessing spins. We just learned about generating a circularly polarized field. And as such, it can coherently push on the bulk magnetization. It's sort of always perpendicular to the bulk magnetization. It can always exert a torque and push the magnetization down. And it's a really, I'll leave this, you can think about it on your own, but the B1 field can continuously push on the bulk magnetization. That means I can create a transverse state of the magnetization. I can keep pushing and invert the magnetization. I can keep pushing until I'm over on the transverse plane on the other side, and I can keep pushing until I'm upright again. And so if I go through that whole process, 90 degrees, 180 degrees, 270 degrees, 360 degrees, I can also do 720 degrees or 1080 degrees. You can keep exerting a torque on the spins, and the spin system will continue to sort of process as it's acted on by that B1 field. Just like the spins will process in the B0 field. So I won't, that's sort of a thought experiment you can think about. If that's really confusing, maybe at the break we could pick it up again. So when we go back to the quantum example here, the idea is that there's an energy difference between the spin down and the spin up state, and that's knowable and relatable to both the gyromagnetic ratio and the B0 field. That's the difference in energy between those two states. On the right-hand side, governed from Planck's law, we know that the energy for radio frequency electromagnetic wave is governed by Planck's constant and the frequency of that wave itself. So now we can set up an equivalence here and just define for ourselves what we call the resonance condition. And it's not a surprising result. It should qualitatively kind of make some sense or be expected already. But it basically just says that to engage this resonance phenomena, the frequency of the RF energy has to be equal to gamma B0. And gamma B0 will, of course, dictate the precessional frequency of the spin system itself. So we need the RF frequency to match the precessional frequency to act and engage this so-called resonance phenomena. Not terribly surprising, but sort of a formal quantum description as to what we're really talking about. And so this is another example also taken from that same Hansen paper. And this is the diagram or the movie that he uses to describe the process of excitation. So we had that state of bulk magnetization that looked like this to begin with, slightly more in the spin-up state, fewer in the spin-down state, and sort of uniformly distributed across the transverse plane, so there's no net transverse magnetization. Through the application of a B1 pulse, this thing is precessing because it's in a B0 field. When I start acting on it with a B1 pulse, I can start tipping over my bulk magnetization. This is very similar to the diagram I showed you before of that sort of spiraling down of the bulk magnetization, right? And in this case, he's showing the spiraling down all the way to the state of inversion. And so, again, you're observing the action of two B fields here, right? Which field is causing the precession? And which field's causing the nutation? B1. Those two systems acting together, they just cause different, they sort of impart a different component of the rotation, of the sort of overall rotation. One of our jobs today will be to go from this coordinate frame. Which coordinate frame is this right now? Lab frame. How do we go from lab frame, where the mathematics I'll show you in a second is a little confusing, skip over that, and how can we get into the so-called rotating frame? And then once we get to the today's great lecture, right? We're going to leave quantum behind, we're going to leave the lab frame behind, and we'll just be stuck in the rotating frame at that point, which is actually a good thing. Okay, so before we actually get there, we'll go for a bit here. I want to talk about SAR, which has come up before. Does someone want to remind me what SAR is, or what it's related to? Specific absorption rate. What's that? It's a terrible word, I think. What's it related to? Why do we care about it? Patient heating, right? And what are the units we typically use? Watts per kilogram, right? Energy per mass, right? We'll talk some about polarization, something about the design of the RF pulses themselves, which imparts better safety, and a few words about B1 safety itself. So we basically covered this already, but this is the idea that we need to define some unit of measure for energy that's deposited in the subject, because of course we can't heat up our patients, for example, more than certain guidelines, or it's uncomfortable, if not unsafe. And I will tell you, the FDA has done a pretty good job of designing these constraints, meaning I absolutely can operate within FDA guidelines and make any one of you sweat, right? So you can decide if that's a good thing or not, but the FDA limit is such that I could put any of you in the scanner, operate within guidelines, and you will feel warm, right? So from my perspective, they found the limit, right? Because you go past that, then of course there's a legitimate safety consideration. The challenge, or a challenge, is that in high field MR, and high field typically refers to more than 1.5 T, not 1.5 T, but greater than. Imaging with high flip angles, where high means sort of greater than 45 or 90 degrees, SAR can really be challenging, meaning a lot of imaging at 3T, the big problems at 7T are all about managing, not the only problems, but several of the problems are about managing energy going into the patients and making sure that they have a comfortable and safe experience and not an unsafe experience. FDA, of course, keeps a lid on all this, but it effectively can limit what you would maybe like to do as a physicist, right? But of course, we listen. Okay, the SAR, not for obvious reasons, but the specific absorption rate is proportional to things like omega 0 squared and B1 squared. So the higher and higher precessional frequencies, the higher the SAR. The higher and higher the B1 field we need higher B1 fields for larger flip angles, for example. If we want to tip 90 degrees, that's why this starts to be a problem, then the SAR becomes complicated. And these things go as squares, so that really sort of makes things difficult. And just through equivalence, if it depends on omega 0 squared, then it's proportional to B0 squared, because those are linked through the gyromagnetic ratio. And we'll see later today how the B1 amplitude is related to what we call the flip angle. The flip angle is how far we push the magnetization over. So, just kind of some rules of thumb about what governs the underlying SAR, and pointing to why it's harder to do imaging with regards to SAR, at least, as the field strength increases. In terms of guidelines, there's different guidelines depending on sort of where you live. IEC governs continental Europe, maybe UK as well. And then, of course, what we mostly care about is FDA. Lots of limits, lots of sort of small details here. Probably the most sort of, the limit we most regard and most sort of encounter is the so-called 4 watts per kilogram over 15 minutes. And if I expose any of you to 4 watts per kilogram for 15 minutes, you will no doubt feel warm. If I do that for less than a minute, you'll say, I think I felt warmer. Might have been in my head. It's hard to tell. And then if we do that for 2 minutes, you'll say, no, I felt warmer. And then if we do that for 5 minutes, you'll want a new shirt. Okay, So anyway, that's where the limits lie. And typically we're really closer, sort of like even the 2 watts per kilogram limits, or even lower. Some MR scans are 0.1 watts or 2 watts or 0.2 watts, and not an issue at all. But it's not hard to get up to these limits, especially because of that quadratic behavior I showed you before. Okay, so there was a fair number of questions about the current that we drive the birdcage coil with. And I said, well, if you really want to know how much current you have to put into the system, depends on having a well-known calibration for your system. So you can say, oh, if I put this much current in, I'll get this much B1 out. Because as physicists that know MR, what we're really going to design for is how much B1 we want. I want enough B1 to tip over my magnetization by 90 degrees, or 20 degrees, or 2 degrees. And so that relationship between current and B1 is not one we can address in this class, because we're not going to get into sort of electronics and system design. But this is one expression for the B1 fields that we would like to generate, right? And there are different possible expressions, but let's start with this one. So here we're saying the B1 field, it's a vector field, right? So it has a magnetic field that's pointing in some direction, and it varies as a function of time, really for 2 different reasons. On the front end here, don't worry about the 2, it just becomes a matter of convenience for later, so fine, there's a 2. And then we have a so-called B1 envelope function, B1e of t. And we'll look at different pulse envelope functions in just a second. But they basically govern how and when we're sort of turning on and off that RF pulse. And is the current constant during that period of time, or is the current following some other trajectory during that period of time? I'll show you some examples in just a second. What's probably a little bit more expected or understood is that we also have to drive, we're going to generate a B1 field that oscillates, choose a function of cosine, according to the radio frequency wavelength that we need, radio frequency that we need, right? The Larmor frequency in principle. And then in fact, we could change the phase on this thing if we wanted to as well. And we'll talk a fair bit about the phase today as well. So there's an envelope function. There's a so-called carrier frequency. That carrier frequency is going to be very different at 1.5T or 3T, right? So an RF pulse you've designed for 1.5T doesn't exactly work at 3T, something to keep in mind. I'll explain a lot more about the initial phase angle. This particular pulse here, we talked about being circularly polarized, right? I talked about having, lighting up those rungs in sequential order such that the B field is sort of circling around. You don't have to do that. You could in fact say, well, I'm just going to generate a B1 field that's linearly polarized, meaning it oscillates back and forth along the X direction or the I direction. And then to do that, I would just need 2 of those rungs. So for 2 of those rungs, I could just oscillate a field back and forth this way without having to chase it around circularly. And so this is what we call a linearly polarized field. We're going to learn in just a second that it's not really a good choice, but it's simple, so we start with that. And remember, B1 is perpendicular to B0. Always, always, forever, and always. Okay, so this is one example of a B1 envelope function. This is just a rect function, right? And there's different ways to sort of show what the RF pulse would look like. So I should have on this axis here said B1, right? So this is B1 as a function of time. And I'm going to turn it on at time 0, and I'm going to shut it off at time tau p. Fine. Mathematically, rect functions are a little bit sort of ugly, right? They're sort of a formal way to express them. All I'm saying here is that there's a B1 amplitude that's on from time 0 until time tau p, and it's 0 otherwise. And this happens to be the, I don't know, what I consider to be inconvenient way of expressing that. So fine, there's a possible rect function. We'll learn later there's lots of details that go into RF pulse design. Actually, we won't learn later because it's an entire course to talk about how to design sort of the envelope functions themselves. We'll cover it a little bit in this class, but not too much. But this is a classic RF pulse. And so what you see here is an envelope function that looks like a sink, meaning it has some oscillation, sort of that's the sort of low frequency oscillation. And then inside of that is the carrier frequency oscillation, right? So this oscillation is a 64 megahertz, or 128 megahertz that has to line up with the underlying Larmor frequency. This envelope function itself here basically controls the spectral information or the bandwidth of the frequencies within that pulse. And that has really special and important properties when it comes to MR imaging. We won't get into it in this lecture. This is just to say there are lots of other possible envelope functions that we could use there. Gaussian functions are possibilities. You're going to have a homework problem that probably uses like a sine function as the envelope. So there's different possibilities there. And we won't get into the details as to how you choose one or the other today, but just keep in mind that that's what we are kind of talking about. So at this point, we've sort of at least heard about circularly polarized and linearly polarized fields. And the idea is, in principle, in designing a system, you could choose one or the other. Linear polarization is pretty simple in its design. It would just be, say, 2 of those rungs, and you'd just be oscillating a B1 field back and forth along the X direction or maybe the Y direction. So it's pretty simple. It's pretty cheap. You'll see in a second, it actually requires higher RF power. So linear polarization is not generally preferred because that SAR problem is even worse with a linearly polarized field. Circular polarization, we generate that with the Quadrature RF transmitter coil, or that birdcage coil. It's slightly more complex, it's slightly more expensive, but it's used in every single MR scanner that I'm aware of. And in fact, they're getting into having multi-channel transmitter systems and things like that now as well, something we won't get a chance to talk about. But the main reason for this is it really reduces the RF power deposition to the subject. And so we can do more. Sure, it costs a little bit more, but it really opens up sort of the RF that we can use when imaging patients, for example. So let's compare the 2 different fields. So again, so transverse plane, just to get us oriented again. So we're sort of looking down the axis of the scanner in the laboratory coordinate frame. I could design a B1 field that just oscillated back and forth, right? That'd still be a useful field. Imagine the magnetization is processing towards me, and every time it comes towards me, I'm able to give it a little bit of a push. And it comes back, and I can push it again a little bit. And it comes back, and I can push it again a little bit. It's useful. It's just not as efficient as having a circularly polarized field, which is constantly pushing on the magnetization because it's chasing it around, right? So this is one example of what the linearly polarized field would look like. I could design a circularly polarized field that looks like this example here. And this just goes back to what we were talking about with the birdcage example earlier. This is nice, so there's different ways to sort of set this up, but I have to have some envelope function. It could be a rect function or a sinc function, doesn't matter. And I have some cosine oscillation along my X direction and some sine oscillation along my J direction. And because of this minus sign, this ends up being a clockwise circularly polarized field. It's on resonance if I design omega RF correctly, and it contributes to excitation, but it also contributes to heating. Right? So maybe not ideal in that sense. Interestingly, I could have another, say, birdcage coil concentric with that one, and I could design a counterclockwise circularly polarized field, right? And in doing so, the only difference here is just the sign in front of the sine term here. And so now I'm changed the phase, if you will, of the oscillating currents. What this ultimately does, it creates a counterclockwise circular polarization. That means it's very off resonance, right? My spins are going at 64 megahertz clockwise, and now I've generated a counterclockwise field that's at 64 megahertz. So they're 128 megahertz different in frequency, if you will, right? So it's very off resonant, and the only thing that does is contribute heating, okay? So why am I showing you this? Well, this linearly polarized field is equivalent to the sum of this clockwise and counterclockwise field. If you just look mathematically at what happened on top here, my sine term changed sign. So I add them together, the sine terms are going to drop out. And I've got a cosine term and a cosine term. Well, I add them together, and I get twice the cosine term. Okay? So what does that mean? Well, it basically means that I can just use this field in the middle here. This is what a modern MR system is going to use, just the clockwise field. And we just simply drop this field. We don't even bother applying or trying to generate that field there. And the point is that I can get nearly equivalent sort of spin behavior out of a system that generates a lot less heating than the linearly polarized system. So this field here is nearly as effective, but its amplitude doesn't have the 2 in front of it, right? So this is half the B1, half the current as the linearly polarized field. So there's a lot less B1 going into the subject to have the same effect on the spin system itself. So it's on resonance, it excites, it contributes some heating, but we've basically gotten rid of all this heating stuff here, and it's this term that gives us equivalence to the linearly polarized field. Big point is that this is the field that we actually use, and principally because it's lower SAR. What's that? Yep. Yep. Okay. So I think sorry, let me just see where we are. I think this will take this will take a few minutes, and then we'll take a break and come back to this free precession stuff. So I've been complaining about the laboratory frame, right? Saying it's inconvenient, it's clumsy, you end up with these kind of crazy terms if you're not careful. Mathematically, we might want to describe force precession in the laboratory frame. We know qualitatively this is what I would be trying to describe, right? How is it that the bulk magnetization traces out this sort of spiral pattern as it falls into the transverse plane, right? So let's quickly look at the equations that would give rise to this, and then agree that we'll throw up our hands and move on to the next thing, okay? It's not that bad, but it's bad enough. Okay, so this is what we would have to start off with. We have the equation of motion on the top here, right? So we've seen this expression before, but now we have two B fields that are acting, right? It's not just the B0 field, but it's the B0 field plus the B1 field. There are two fields, they're on. B0 field, we never turn it off. B1 field, once we turn it on, by superposition, we have to have them both active, if you will. And we just saw in the previous slide the form of the B1 field. A possible form, at least, is that it has some function, it has some envelope as a function of time acting on the I direction, if you will. And it also potentially has some term acting on the J direction. The B1 only acts on the I and J directions. It's perpendicular to the K direction. And then we have to give our B0 field in here again as well. So this is sort of the, we've set up the problem at this point. We've said we have a spin system. This is our B field that's being exposed. And now we're left to setting up the system of differential equations that falls out of that determinant, okay? And so we just look at the first term, dmx dt, and we say, okay, fine, I have to do the determinant of this guy, and I'm going to have a gamma b0 times my, that's gamma b0 my here, and then I have to take the negative, I have to subtract off this term here, and I get a minus gamma b1 times mz, and that's my minus gamma b1 times mz. So do you guys understand how I have to elect the field I'm going to use, and then I have to take the determinant to get my system of differential equations? We're going to see this several times. I'll work through it a little bit more carefully in a different problem today. But this is the setup. Now, what's the problem? The problem here is that I have my mx magnetization. How does it change as a function of time? Well, it depends on my. Okay, that's not so bad. We saw that before. But it also depends on mz now. Okay, so now we've got this like super coupled system of differential equations. And my my is no better. My depends on mx. And my also depends on mz. So every component depends on every component. It's kind of it's a hassle if nothing else. And then lastly, my mz magnetization depends on my mx magnetization and my my magnetization. So there's reasonably complex coupling here. If you look back at what was happening, it was just a sort of spiraling down of the transverse magnetization. That's not so bad. You could probably guess at a solution to that. But let's just leave it at the fact that this is relatively complex coupling for that system of equations. It gets even worse when we now try to plug in, well, what is our actual B1 of t? Well, our B1 of t is some envelope function. It's got some cosine term. It's got some sine term. And the whole thing just gets to be a little bit more complicated. So again, we can deal with this. We could solve this if we wanted to, but we could also agree that that's pretty complicated. And in fact, describing the bulk magnetization's behavior in the laboratory frame doesn't give us the same kind of insight that the rotating frame does. Because oftentimes we don't really care about what's happening at 64 megahertz. We just care about what's happening in the rotating frame. Did the spin end up over here? Did the spin end up over there? I don't care that it was also going at 64 megahertz. I sort of know that's happening anyway. And so the point is complicated. Let's not worry about it. Let's go ahead and focus on getting ourselves into the laboratory frame. And so we'll go ahead and take a break right now, just for a few minutes, and then we'll come back and talk about how we get ourselves into the so-called rotating frame. And then hopefully there's time that we can work through a couple of examples as well. Cool? Okay. Happy to take questions for a few minutes or whatever. We'll take a 5-minute break and then get going again. Yeah.
In the laboratory frame, it looks like a little bit difficult to imagine that B0 has so large amplitude, but B1 is so small.
Yeah.
Tipping is so large.
Yeah.
You can still tip a 90 degree, but in the rotation frame, it looks like it is possible because B0 is basically kind of removed.
Yeah.
So
they're just happening at very different time scales, right? And so So we saw that B1 is really small field, B0 is very high field, right? Tesla, micro Tesla, right? So, but of course the spin system is you know, it's going to feel the effects of both of those fields, right? And so when we turn on those two fields, you know, there's 6 orders of magnitude difference, right? So in some unit of time, a millisecond or something like that, it will process around like millions of times or hundreds of thousands of times, but it will only tip over maybe a quarter of a hertz, a quarter of a cycle, because it's such a weak field, right? And it does it, so it's tipping over very, very slowly because it's a very weak field. Does that help? And they're perpendicular, so it doesn't really matter, right? Like, you know, B0 can be any magnitude and B1 can be any other magnitude. If they're perpendicular, they have independent effects.
Right, yeah, and I figure that when we try to do the addition of these two vectors, we cannot use the B1 amplitude at the B0 amplitude because they're in different frequency scale. So
well, yes, but they do, physically they superpose, right? So B0 is this big vector this way, and B1 is this little tiny vector this way.
Right.
They just have different, you know, it's the I component or it's the I and J component versus the K component.
Yeah, but I also remember that last time you mentioned that it always precession around the B0 plus B1, a total field.
Yeah.
Right? So if we can add these vectors together, then it would be really like tilting a little bit, saying the precession would be
No, I don't agree. So tilting, how much it tilts, is just the integral of the frequency over time.
Right. Okay, yes, correct.
Right?
Yeah.
And so it has a high frequency for precession, so it goes through thousands, millions of cycles, and it just goes through a quarter of a cycle. Right?
Okay,
There's just completely different time scales. But it's not. But that's, you have to think of it that way.
Okay, yeah.
It's not that the, you know, if what you were talking about was B0 points along K and B1 points along K, then B1 wouldn't matter because it would just be this tiny little vector on top.
Right, correct.
Right?
Yes, yeah.
Yeah.
Thanks.
No, it's those good questions. None of it's easy. That's all I could say.
For this, do we have following courses that can, for the MRI area?
Yep.
Oh,
There's a couple. So next quarter, I'll make an announcement about that right now, actually, just because it might be of interest to lots of people.
oh, okay.
Is that cool?
Yeah.
Yeah. Okay. Good. Alrighty, guys. I know it always goes fast, but you know, as per usual, I'm sort of halfway through the material I want to cover in 2/3 of the time, right? So we'll figure this out. So one of the questions during the there were two good questions during the sort of break there. One I'll leave as a thought experiment that I want you to think about. And I get this question most years, and it's sort of a question about, well, how is it that you have this crazy strong B0 field? How is it that this little tiny weak B1 field can do anything, right? How is it effective at acting on the spin system at all? And the simple answer I'll give you right now, and we can talk about it more as needed after class, whatever, is they're perpendicular fields, all right? So B0 is causing a torque around the z-axis, and B1 is causing a torque somewhere in that transverse plane. And as they're perpendicular B fields, they have independent orthogonal effects on the B1 system. And so their strengths don't matter. What their strengths govern is how many cycles are going to happen per unit time, right? There's an omega 1 for the B1 field, and there's an omega 0 for the B0 field. B0 and B1 are different by 6 orders of magnitude, Tesla versus microtesla. But the key is that they're orthogonal fields, perpendicular fields. So if that doesn't click or make sense, then just find me after lecture. We could talk about it some more. I can wave my hands around more. The other question was, are there other courses related to this that follow on from this? And the answer is yes. For the past several years, fall, winter, spring quarter, there's been a class called 229. I don't remember if it's multi-listed or not. It's at least in physics, biology, and medicine. It might be multi-listed under bioengineering. If this material interests you, if you're going to work in an MR lab or do something related, definitely take that class. Very good class taught by Holden Wu and Kyung Sung, maybe some guest lectures as well. There are a couple other courses, and their offering is a little bit more variable. So you could look for 225 and 222. Those are the ones that I know of off the top of my head. Okay, questions before I sort of get into the I know you're just dying to hear about the rotating frame. Okay, let's do it. Okay, so this is what we've been talking about for a long, long time, the laboratory coordinate system. I think you get it at this point. It's me standing next to the scanner and describing what happens to the spin system. And we said, well, there's going to be some rotational angular velocity that's governed by minus gamma times B0 K. The minus sign came out of solving some equations a while, maybe last lecture or the lecture before, that really just indicated to us that this was a left-handed precession. Right? That's a little bit unexpected because we're so used to using the right-hand rule, but the precessional behavior of protons that have a positive gyromagnetic ratio is such that they have a left-handed or clockwise precessional behavior. Okay? B1's going to force it to work to move in a clockwise manner. B0 is going to do the same. That's just the physics of the problem. If your gamma was negative, and that's possible, some spin isotopes have a negative gyromagnetic ratio, then they're going to be precessing with the opposite handedness. And I'm sure that screws people up if you work in that field. Okay, so what's the rotating frame all about? Well, the idea, again, I've said it several times, we want to simplify the mathematics of MR. And the idea to have in mind is that if the rotational frequency of the rotating frame, right, the coordinate system itself, is matched to the bulk magnetization's precessional frequency, then the motion of the bulk magnetization is removed, or sometimes I refer to it as being demodulated. It's like getting on the merry-go-round. We're going to spin with the system, right? And consequently, rotating frame's transverse magnetization plane rotates clockwise in this left-handed manner according to some frequency omega. And so this is the coordinate system we're going to be in, right? We're going to be rotating with everything and observing the behavior of the spin system from this rotating frame of reference. And that's going to make our life a little bit simpler from a mathematical perspective. And when the math gets a little bit simpler, then you have more insight to what's actually happening in the problem. And then you can always remind yourself, oh, that's right, everything's zipping along at 64 megahertz as well. This is what I'm really getting at. We've seen this example, this is the third time today. In the laboratory frame, the bulk magnetization sort of maps out this spiral trajectory. We just a second ago saw the system of differential equations, these coupled equations, that would actually describe mathematically this behavior, and we just said, that's all right, looks complicated, we'll go to the next thing. The next thing is the rotating frame. In the rotating frame, that same RF pulse just maps out this, right? Much more simple, much easier to understand that when I say, oh yeah, this is a 90-degree pulse, you might say, okay, I'll take your word for it. Here, it's much more clear that that's a 90-degree pulse. We've done something to act on the spin system such that it rotates a total of 90 degrees. Now, the interesting thing, and we'll learn about this just now, is that how far it rotates is something we can control. And in fact, the direction that it rotates is something that we can control. So we can talk about the flip angle, how far it rotates. We can also talk about the phase. I can bring my bulk magnetization down along the x prime axis, or by manipulating my RF pulse, I could bring it so that it comes down along my y prime axis. Why you want to do that? We won't talk about that too much in this lecture. We'll just talk about the how we can do that problem right now. Oh, and importantly, notice that both these coordinate systems share the same z-axis. That also makes our life a little bit easier, right? So the z-axis or the z-prime axis, this is sometimes the k or the k-hat prime direction. Those are equivalent. We haven't done anything to change that direction, so that's simply shared. And that'll make things a little bit easier as well. So mathematically, and there's a lot of, there's detail in this. I've tried over the years to discuss this in slightly different ways. And rather going through the full-blown derivation, which is a bit dry and a bit detailed, I'm going to take kind of a higher level approach. And basically just say that the unit directional vectors that we use to describe either the laboratory frame, or sorry, the rotating frame or the laboratory frame, there's of course a transformation between those two coordinate systems. And it looks a lot like a rotation. If you look inside here, you've got a cosine on the diagonal, if you will, and sine term on the cross terms. And it's just saying that if I want to know what my rotating frame coordinate vectors are, I can get those by multiplying effectively the direction vectors in the laboratory frame by some carrier frequency, cosine omega t or sine omega t. And of course, there's an inverse transform as well. If you know rotation matrices, the inverse of the rotation is just the transpose. And so you can see here, the only thing that changes is the location of the minus sign flips, right? So now the minus sign is down here. So this is just by definition, and we'll need this a little bit later. Importantly, we can write down, for example, a B1 pulse in the laboratory frame. If we want to write down that same pulse, but in the rotating frame, we have to update how we write down each of the component terms. So if I know the I, J, and K components in the laboratory frame, rather, if I know the I, J, and K components in the laboratory frame, I can figure out what they are in the rotating frame through this transformation. So I can go back and forth between those coordinate frames. And believe it or not, this will actually make our lives a little bit simpler. We also need to be careful about sort of nomenclature here a little bit. And so we can talk about the bulk magnetization in the rotating frame. So I'll subscript it as rot. Eventually, we'll just drop that because it just gets to be cumbersome to sort of carry it all the way through. And so we just talk about having x, y, and z components, but they're the x prime, y prime, z prime components. Same thing for the B field. We have some B field. That B field is applied. We can choose coordinate systems to describe it in. We can choose to do it in the rotating frame, and then it's bx prime, by prime, bz prime. And again, because that z component is shared, then those components are equivalent, right? Any z component we have is equivalent in these two coordinate systems because that part hasn't been changed in any way, if you will. That I said already. It's okay. Okay, so there is a very formal way to get to this expression here, and that's what I'm skipping this year because that's when the most people drifted off, according to my notes, right? So we're going to skip it a little bit. If you want to, I don't know if you guys have found the YouTube channel yet, but last year's lectures are there. If you really want to see the derivation, it's probably in last year's lecture. I'm quite sure it is. The bottom line is I just want to make a comparison right now for the equation of motion for two different coordinate systems. This we saw already, right? The laboratory frame coordinate system. It updates slightly when we talk about expressing this in the rotating frame, right? In the rotating frame, we have to, importantly, we have to talk about the bulk magnetization in the rotating frame. It's the same magnetization vector. It just has different components because it's a different coordinate system, right? So it's the same vector. It's the same physical thing, but its components are different depending on the perspective that you're looking at it from. The other thing, and this is the less obvious thing, we have to add in is this omega rot divided by gamma. And this is effectively what demodulates, right? Omega rot divided by gamma is related very closely to the externally applied B0 field, right? Because we know from the Larmor relationship that that omega equals gamma B0. So we'll see in specific examples what this sort of term does. And so this term is always going to be there. This is what effectively transforms us into the rotating frame, is simply including this term here. The next thing we have to do then is define what is the B field in the rotating frame. And you'll see how this ultimately simplifies a little bit. So again, the only thing to really remember from this right now is that adding this term and changing our nomenclature a little bit is what puts us into that rotating frame. And you'll see how that becomes a useful thing in just a second. Sometimes we can make this substitution where we just collect these two terms and we call it the B effective. And so the effective B field in the rotating frame is just the sum of those two fields. This so-called fictitious field that effectively demodulates the effects of B0 and then the actual applied B field in the rotating frame. It'll be a little bit more clear probably when we work through an example. But if you really want these top two expressions to look equivalent or nearly equivalent, then you can substitute B effective in for this sum here, and then it sort of term for term lines up with the above expression. The trick that we have to work through sort of through some examples is really understanding like what do we use for B rote, or what do we use for B effective, or for M rote, so that we can actually work with this system of differential equations. So not obvious exactly how we got there. This is the important term. Let's see how it helps us. And then just by substitution, you can get to this simpler expression, if you will, for the equation of motion in the rotating frame. Okay, so the two examples that we want to work through, first one is free precession in the rotating frame. I'll do a clock check, see where we are with time, and then hopefully we'll be able to talk about, no, we'll get through both of these because the first one's really quick. And then we'll talk about forced precession in the rotating frame. And again, that's with a coordinate system that's anchored to the spin system. And then we'll work through those couple of examples, and then I'll see if I make it back to the slides. I got to get through those two. If we don't get back to the slides, we'll figure that out a different way. And of course, we're not worried about relaxation. Okay, so you guys okay with the starting point? Okay, because I'm going to put this up, and then we're going to work on the board for a bit. Okay. Okay, so just to be clear, this is going to be free precession in the rotating frame. And we haven't gotten there yet, but this is still without relaxation. Okay, so we're going to start with the same conditions that we normally start with. We're going to say, well, we know that our B field that's applied is just the B0 magnitude along the K direction, right? And we said between these two coordinate systems that the K direction is shared, and so that's equivalent to B0 in the K hat prime direction, okay? Now, that in turn is equivalent to B in the rotational coordinate system. What does that mean? Well, it doesn't matter which coordinate system I'm talking about, right, for the B field. The B field only points along the Z direction anyway. And so my B field, if you want to think about this as being in the lab coordinates here, right? The B field I have in the lab coordinates has the same component description in the laboratory frame or in the rotating frame. This is going to end up being a little bit trivial, but I want to use it as a starting example, okay? So then the question is, to use that equation of motion, we have to describe the effective B field. What's the effective B field in the rotating frame? And so our B effective, we define this, right? This is not anything new except for as it was presented in the last slide. Depends on omega rho by gamma plus whatever our B rho is, whatever our B field is in the rotating frame. Okay, so how do we make use of this B effective? Well, we need to remember the original expression we had for the angular velocity, right? In the laboratory frame, this was just minus gamma B0 along the K hat direction. We know, again, from what we just showed, that that's going to be the same as minus gamma B0 in the K hat prime direction, right? The K direction is shared, so these are just equivalent expressions. And this itself is just omega rho. This is the definition, this is by definition the angular frequency that we would describe in the rotational coordinate frame. It just depends on gamma B0 along the K hat prime direction. Okay? And so we know what B root is, and we know what omega root is. You guys okay with that? So now we just have to come back and define B effective based on the conditions that we described, right? Just having only an externally applied B0 field. And so now this expression here, we have omega root. We could pick any of those, but we really want to start by something that's in the rotating frame. And so we choose minus gamma B0 along the k hat prime direction. And this is just divided by gamma. And then we have plus B root, but B root in the rotating frame was just B0 in the k hat prime direction. Okay, so what just happened? What do we have as the final B effective? 0, right? So not a terribly interesting case. You guys probably got there before I did, right? So what's the point? Well, the point is that in the rotating frame, if all you have applied is the B0 field, there is no effective field. We've demodulated, gotten rid of, canceled out the effects or the apparent effects of the B0 field, right? We can use that now. That B effective can go back into that equation of motion and describe for us what's happening under those conditions in the rotating frame. Question? Everything I'm describing now is just one rotating frequency. Yeah, single isochromat, one spin frequency. We can generalize this. It gets more complicated, but and in fact that's done in the book, but we won't cover that here specifically. Not now. That's a good question. Okay. Right. So now let's come back to the equation of motion that we had, right? And the equation of motion said something like dm rho dt was equal to m rho cross gamma. We could write this in different ways, but I'll go ahead and write it as omega root by gamma plus B root. Right, so that was just our expression, the equation of motion in the rotating frame. Now we can plug in, we know what that term, what the B field term is after the gamma over there. So we end up with, not an interesting solution, but good to work through it for thoroughness. We have m rho cross gamma times 0. And so we could write out the whole system of equations for this. It wouldn't be terribly interesting. We would write this out as a cross product. We would say, well, I in the I hat prime, j hat prime, k hat prime. Our m vector would be the m x prime, m y prime, m z prime. And then the effective B field would be 0, 0, 0. And this would give us a way of getting to the system of equations that describe spin behavior in the rotating frame. So what does this determinant expression say about each of the components of our bulk magnetization in the rotating frame? They're constant, right? Whatever they are, however they got to be there, they're just constant. Trivial situation, again, maybe not terribly interesting except mathematically, but if you carry this through, you'll end up with 3 differential equations whose time derivatives of these components just equal 0, because every determinant product in here is just going to be 0. Okay, fine. So a simple case that at least helps us appreciate maybe that working in the rotating frame is a little bit simpler than the situation that we had last time with free precession. Last time we had free precession, we had non-trivial terms across the bottom here, and we ended up being able to mathematically observe that the transverse components would be oscillating back and forth, or around and around rather, at the Larmor frequency. Questions about sort of how I worked through this? So the next step, just so we're all on the same page, the next, I'll write down a couple steps for how we're going to get there. It's going to take a little bit more work because we're going to end up with something non-trivial for our B effective here, and that's going to give us a system of equations that we can talk about solving or not solving. I might jump partway to the solution. Okay? So I'm going to clean this. Okay. I Actually, I'll leave my label because I'm just going to update one word. Okay, so we're going from free precession. What are we going to do next? Forced. So there's a couple steps that we procedurally have to work through. I'll make some short notes here, and this will set us up. So there's kind of 3 steps. The first one that we want to do is define, well, here, I'll just try it. We want to define our B1 of t in the rotating frame. So we're going to set up some general B1 function, but then we have to move it into the rotating frame coordinate system. That's the first thing I'll work through. The second thing that we have to work through is we have to define B effective. Same in the rotating frame. And the third thing that we have to do, I think, before we get to talking about a solution is then define the equation of motion. So depending on how I can use the board over here, these are sort of procedurally the steps that we're going to work through. So the first one is to talk about what's the B1 function that we maybe care about. And in the general sense, the B1 function, B1 as a function of time, is easily described in the laboratory frame. That's what we just talked about. We talked about this RF birdcage coil and oscillating currents and setting up a B1 function for that field. And so we have some B1 envelope function, which can be a function of time itself. And then that's multiplied onto 2 terms, a cosine and a sine term. So we have a cosine, say, of omega RF times time, plus, in principle, there could be some phase. We haven't talked too much about the phase yet, and in fact, we'll leave it out in just a second. But for completeness, there could be some phase associated with this as well. And then the second term is minus a sine, otherwise looks equivalent, so omega RF times time plus some phase. And instead of being on the I direction, it's on the J direction. Okay, so again, this is in the lab frame. What we want to get to is B1 in the rotating frame. If you go back to your notes, we saw this just a second ago, but we said that the I hat direction was equivalent to cosine omega RF times time on the I hat prime direction plus sine omega RF times time on the J hat prime direction. This was just the definition that connected us between the 2 coordinate frames. And we had something similar for the J direction. It looked like a minus sine omega RF times time on the I hat prime direction plus a cosine omega RF times time on the J hat prime direction. So these 2 things here, these are just by definition. If you go back 5 or 6 slides, you'll see them there. So all we have to do to begin with is just plug in an expression for our I hat direction into here, right? So this is just going to go into here. And we have something similar for J, and it's going to go into there. And so we'll end up with something that's a little bit cumbersome, and there'll be some it's no surprise when you start working with sines and cosines, you start looking for trig identities and things like this, and that's perhaps no surprise what's going to happen. In substituting these in, what it allows us to do is transform B1 of t into B1 rot. t. And that's the first thing I said we have to do. We have to define B1 in the rotating frame. And so what does that look like? Well, the first term is just B1e of t. And now we've got this cosine term and the sine term. I'm going to write them out. Well, I'll just write them out. So we still have the cosine of omega r f. Let's drop the phases, because this will make our life a little less crazy. So we just have omega rf, oops, times time for this term here. We'll just leave the phases out. We can let them just be 0 for now. And now we're going to substitute in for I hat, this whole expression here. And so we have a cosine of omega rf times time along the I hat prime direction. I'll get out of the way in a second, plus sine omega rf times time in the j hat prime direction. There's going to be a second term that we have to add to this. It's going to be a minus term, so we'll have a minus sine of omega rf times time. That's just this term here without the phase. And now we substitute in again, if it wasn't clear, this term here, right? That's just I hat. And now I'm going to write in a substitution for j hat, and I have a minus sine omega rf times time along the I hat prime direction, plus a cosine omega rf times time on the j hat prime direction. And this expression here is just for j.
What happens to the phase?
For now, I said let's just go ahead and let it be 0. No reason to necessarily do that. It'll simplify things for us a little bit just to let it go. We'll talk about the phase later, like the importance of the phase later. Okay, so if you look at the terms that we have here, right, we have a cosine times a cosine term. That looks like a cosine squared term. We also have a cosine times a sine term. And then we have to be a little bit careful on the bottom here. We have minus sine times minus sine. That looks good, so we have a sine squared term. But we also have a minus sine and a minus cosine. So we have a minus sine minus cosine to go with our cosine minus sine. So there's two trig identities that we can take advantage of there. One, we can simplify this because we know that cosine times sine minus sine times cosine is just equal to 0. And if you carry out the multiplication, you'll see that those terms are there. And the other one that's handy is, of course, that cosine squared plus sine squared is equal to 1. And we have that situation as well. Can you see that? Okay, so why is that such a good thing? Well, when we're done, the idea is that in the rotating frame, our RF pulse has gotten to have a slightly simpler description, and it just looks like B1e of t, same envelope function, but simply oscillating or doing whatever that function is doing along a single direction, the I hat prime direction. So all of these terms sort of collapse to a 1, and some drop out as a 0. Okay? So this is actually really nice, right? Because this just says, if we're talking about what the B1 field does in the rotating frame, it really just depends on that envelope function. And that's why there are entire courses on designing the envelope function. No joke, not here, unfortunately. I wish we had one. But about how do you design that envelope function to get the spin to do what you want it to do. And there's lots of reasons why you may or may not want the spin to do something, but there's a whole design strategy involved there. Yes?
But that is only the case when phase is 0.
That's correct. Yeah, it ends up not being that much, this doesn't end up looking all that much different if we have a non-zero phase. That used to be a homework assignment. I'm not sure, I think I took that one out this year, so you probably won't see exactly how that comes about. If you leave the phase term in there, you can still end up with a very simplified expression. Okay? What it ends up looking like, what you've done at this point is you've said, oh, okay, I'm only pushing my B1 along a single direction. If you leave the phase in there, you'll end up with a B1 envelope function projected onto the I and the J direction. And you'll just have a cosine related to the phase term that's on there. cosine phase and a minus sine phase or something like that. Yeah? Okay. So that's only part of our job, right? So at this point, we've done this one. We define the B1 in the rotating frame. And so let's keep it over here. So we said that our B1 envelope, or sorry, the B1, I have to erase what's up there. It's some bookkeeping here. So our B1 field in the rotating frame as a function of time is just our B1 envelope function as a function of time on the I hat prime direction. Okay? Okay, so I'm going to clear this so we can get to the next step. Cool? You're not convinced yet that this is worth it. Okay, so the next step is that we want to define the B effective in the rotating frame. So how do we go about doing that? Got to find the right node. Yep. Okay, so we saw this a second ago. We said that the B effective is defined as, right? So it has this definition that it's omega rot by gamma plus B rot. Unfortunately, we just figured out what B rot is, so we're getting there, or at least we figured out the B1 component of that. This term here, again, if the understanding is that we're just exposing the system to the B0 field, that's what governs the difference between the laboratory and the rotating frame, then this term here, when it's useful, this can just be equivalently the gamma B0 along the K hat prime direction divided by gamma. It's a somewhat complicated way, but it's sort of mathematically motivated that this term will basically just subtract out the B0 field, right? This is what demodulates anything that shows up in B rot. Now we have to talk about B in the rotating frame in just a second, but this is that demodulating term, and it's going to always look the same so long as we're talking about demodulating by the B0 field. It could look different if you were trying to do something slightly different. Okay, so now we have to talk about the B1 rot here. And in the rotating frame, we still have two fields, right? We have to take account for the B0 field, and we have to take account for the B1 field. Remember, this is mathematically convenient. It's a fictitious field. It doesn't really exist, right? It makes things convenient for us. Now we have to talk about what actually exists. And in terms of what actually exists, we have to talk about the B field in the rotating frame. We know the B0 field in the rotating frame just looks like B0 along the K hat prime direction because that K direction is shared, nothing new. And now we have to add in, for example, the B1 field. But we know what B1 in the rotating field is. That's what we just did a second ago. And so we know that looks like B1 envelope function as a function of time along the I hat direction. So this is the applied field, all fields, as described in the rotating frame. This is just a convenient term. Right? Yes. Yeah, this is the resonance condition. We can talk about, and there are useful reasons to do so, to talk about things that are slightly off resonance in different ways. But here we just, for now, keep it simple. It's maybe complicated enough at that, right? Okay, so easily done. So this term here just ends up looking like a minus B0 along the K hat prime direction. Inside here you have a plus B0. Sorry, that didn't need a vector on it because it's a B magnitude on a K hat prime direction, plus just the B1 effective field, or the envelope function rather, on the I hat direction. And so, what's that? At this point, it's got to be, right? Because that was the whole point. Yeah, so there should be a prime there, and there should be a prime here. Thank you. And then you can see those terms are just going to cancel out, so then we just have that it's the B1 envelope function as a function of time on the I hat prime direction. And now that we've defined these two terms, so here, just for bookkeeping, I'll write that my B effective is just equal to B1 envelope function as a function of time along the I hat direction. So now we've gotten through these first two steps, right? And the last thing we want to do is at least define the equation of motion and then talk about solutions. That's our goal, right? How do we describe the bulk magnetization once we know what the governing equation is? Yeah? It's okay, Johan?
I think it's more intuitive just think you have a fictitious inertial B field cancel out the original field.
Yep. No, and that's exactly right, right? So this term here, what I sometimes have been calling the fictitious field, right? What Zhao Han said is that just this term here just cancels out this term here, right?
Because you have an inertial frame, non-inertial frame.
Yeah, I wouldn't say inertial frame, but you have a rotating frame, right? A different frame. Maybe you're thinking about it a little bit differently, but that's the goal of setting it up that way.
Yeah, but I think that's equivalent to an inertial force, right?
Well, it depends what you mean by equivalent. I mean, we're not talking about even masses at this point, right? So I don't think of it as an inertial frame, but maybe that's a pure physics term.
Inertial frame, right?
What's that?
And rotating frame is not an inertial frame.
No, I don't think so.
Then
Yeah.
you have a non-inertial force in it, right?
Yes.
Then it acts like the minus term.
Yeah, sure. Yeah, okay. Yeah, yeah. I don't know if that's useful for everyone. That's like a very physics description, but same. Point being that they are going to cancel out each other. But they cancel out each other because we've defined what system we're talking about in the first place. Yeah? Okay. Okay, so I'm going to clean this up, and then we're going to look at the equations themselves and hopefully get to the solution. So we come back to the equation of motion, which is that sort of cross-product determinant-looking thing, right? But now we actually know what our B1 fields are, and more importantly, say our B effective field is, right? And so the starting expression for that, again, was, well, we'll go to here. So we'll say that the dm rho as a dt, right, is governed by m rho cross product with gamma b effective. We saw this at the end of one of the last slides, but now we know what B effective is. And so this just looks like M rot crossed with gamma B1 envelope as a function of time along the I hat direction. If we carry this out to the sort of full determinant form, which for me at least gives me a grasp on how to write out the various terms. We write our unit vectors across the top. Our m rho vector components go across the middle here, so that just looks like m x prime, m y prime, and m z prime. And now we have to add in our B1 field here. And so we only have one component. It only falls into the I category, if you will. That should be a prime. And so we have a B1 envelope of T here. And we don't have any J component to our effective B field, and we don't have any Z component to our effective B field. Yep, sorry, there should be a gamma in there. It's even in my notes. So don't miss the gamma just here, right? And this actually looks very familiar. This is where, you know, I know I'm sure I'm going fast enough, but this is where I might skip one or two steps because it looks very much like what we talked about before in terms of having a coupled system of ordinary differential equations. When we looked at it the first time, it was in the laboratory frame, and we just had a B0 term hanging out over here, and that meant our mx and my terms were coupled. Now we have a term that's hanging out over here in the x component, and it means that our x and z components will be coupled, but our y component will be sort of out of the picture, if you will, for this specific case. I'll go ahead and work through some of this, and then I probably won't work through how we get to the solution too carefully. But from this system, again, this represents a system of differential equations, right? So we could write the first one just to say that we have dmx prime dt is equal to. So we're talking about my times 0, my prime times 0, and mz prime times 0. And so this just equals to 0. And so under this specific set of conditions in the rotating frame, our x component is just constant as a function of time. That B field's not doing anything to act on the x component specifically. Similarly, and this is what we did before, we can write out what's our d my prime dt term. And the my prime term has an mx prime times 0 minus this mz term and this gamma b1 term. And so it looks like, is there a minus sign in there? Oh, no, there's no minus sign, right? So then it's just a gamma b1 e of t times mz prime. And then just for completeness, we can write the last one here on the bottom. Sorry if it's a little low. dmz dt. And it's similar, but this one has the minus sign. So minus gamma b1 e of t times mz prime. And so here, again, these two expressions here, these are the coupled ones this time. Yep. Yeah, you're right. So it has to be coupled. Okay? So we saw something very similar to this before. The difference here is that we had a constant before. We just had a b